So when it says how many necklaces are possible from 2 gold, 3 blue, and 5 green, let's write that down. 2 gold, 3 blue, 5 green. There are some things we need to talk about in that. Assuming that all the beads are different, how many necklaces with a clasp can be made? Now, I want you to think about this for a second. Does anyone have a necklace on today with a clasp?
What's a clasp? They got holes.
Yeah. Okay, you got one on, okay?
Take it off.
Now, when you put that necklace on, how did you put it on? Exactly. So take it off. Can you do that? There you go. Stop right there. Hold it out like this. When you put a necklace on or a clasp on a necklace, it is no longer a circle. When you put a clasp on it, what does it become? A line. Because the reason we subtract 1 when we do circular permutations is because circles have no beginning and no end. So those rotations are not separate arrangements. As soon as you put a clasp on it, now it's broken. And it has a beginning and an end, and it acts like a line. So when we have 10 beads and a clasp, it's 10 factorial. Again, as soon as you put a clasp on a necklace, thank you, Dylan, it is no longer a circle. It is a line.
So, wouldn't it be a line when it's not clasp yet? Right?
That's what we said. Yeah, the clasp breaks it.
Okay.
The clasp breaks it. So it becomes linear. So 10 beads and a clasp is 10 factorial. But there is one more consideration we have to make.
Whoa,
I know.
You have to divide by 2, 3, and 5. Factorial.
Does it say the beads are identical?
No, they're different.
It says assume they're all different, so there would be no division. Now, if they were the same, we would divide, but they are different. There is still one consideration we have to make. Let's suppose I have on a necklace, and I have, I don't know, I have a pink bead, and a green bead, and a yellow bead, and an orange bead, and a red bead. Okay, here's my necklace, all right? I'm wearing this necklace. You're looking at me, this is what you're seeing. Okay? Now, if I take that necklace off, alright, so I'm wearing this necklace. This is what you see. I hold it out here in front of me. I take it off, hold it out here in front of me. This is what you still see. But that's what I see. Why? Because I'm looking at it from the other side. That is called a reflection. Did I make a new necklace?
No.
Did I rearrange anything? No. I simply looked at it from the other side. When you have, and this sounds complicated, but it's not, they're called handheld circular permutations. When you have handheld circular permutations, necklaces, bracelets, keychains. Basically, that's it. Necklaces, bracelets, keychains. When you have those things, you have to divide by 2. Because the fact that you can hold it in your hand means you can look at it from both sides. And the arrangement looks different when you draw it, but it isn't. It's the same arrangement, just looked at from the opposite side. The only problems you have to worry about dividing by 2, now listen so it doesn't get all convoluted in your brain. The only problems you have to worry about dividing by 2 are necklaces, bracelets, and keychains. Okay? That's it. So if somebody says how many ways can you arrange 8 keys on a key ring, it would be 7 factorial divided by 2.
Was that with the
Wouldn't
class
it
or
be
with?
with or without it?
Assuming a keyring doesn't have a clasp. Normally you don't put clasps on necklaces
Wouldn't
and.
it be 8?
Brenton, 8 keys in a circle is 7 factorial.
Oh, you're right.
I need you to not confuse everybody, okay? You're asking.
I'm not trying to.
I know, but why don't you just hang on and ask me after class, okay? Alright, so here we go. B. I want all beads to be different, but no clasp. Alright? So now I have 10 beads, no clasp. 9 factorial divided by 2. Beads in a circle are going to be 1 less factorial unless you put a clasp on them. All the beads of the same color are identical, and there's no clasp. This is what Burkhart was talking about. If there's no clasp, I'm going to start with 9 factorial. I'm of course going to divide by 2 because it's a necklace, and all of my necklaces, bracelets, and keychains get divided by 2. But what else am I going to divide by?
2, 3.
2 factorial, 3 factorial, and 5 factorial. Why?
They're all identical.
Because the beads of each color are identical. All the beads of the, oh good grief. All the beads of the same color are identical. The blue must be kept together, and there's a clasp. Alright, so let's just catch all that. There's a lot going on. Okay. The blue must be kept together.
Alright.
So I'm going to tie a string around these. They are now 1. So I have 2 and 1, that's 3, and 5 is 8. Now, I'm putting them in a circle. Is there a clasp?
No.
Yes. So 8 things in a circle with a clasp is 8 factorial. There's my 2. I'm dividing by my 2. Now, what else do I need to include in the problem?
3.
The 3 at top.
On the top, there's going to be a 3 factorial. Why?
You got
That's
3.
my bundle. That's my bundle, right? Just like, remember when I sat the boys together in a row, I had to multiply by boys factorial? Now I'm multiplying by blue factorial. What else? I gotta divide by 2 factorial, 3 factorial, and 5 factorial, because why? The beads of each color are identical. Oh my gosh, there's a lot going on there. Okay. On average, Mrs. Ford has to wake someone up during 5th period once every 3 days. What is the probability that she will wake someone up once in the next 5 days? Mallory. You know exactly what I'm going to say to you. No. I don't want it, but it really is going to get it attention. You guys are addicts. I don't understand that. Alright, here we go. Any thoughts on how to do this problem? It could be a tree diagram. The problem is, since you're going for 5 days, it's going to have a lot of branches. A lot of branches. So I think I won't do it with a tree diagram, although it could be done that way. Any other thoughts on how to do it? I would do it that way. I think of it as a binomial probability problem. So I would think about the 5th row of Pascal's triangle. And why am I going to the 5th row? Because there's 5 days. I'm going to, wake somebody up or not wake somebody up 5 times, or on 5 different days. This number would represent what in terms of this problem? This is waking somebody up every day. So this is 5 wakes. This would be 4 wakes and 1 not wake. 3 wakes, 2 knots, 2 wakes, this is the number I want, 1 wake, 4 knots. Would you agree with that? Exactly 1 wake up? That's the number I want. So I'm gonna write down my 5, that's the number I want. Now, in this problem, what's happening is, I am waking or I am not waking. Every day, I wake or I don't wake. Now, what's the probability I'll wake someone up?
1 out of 5.
Watch it. Read the
It's 1
bold
every 3
face.
days. So it's 1/3.
1/3. And then the probability I don't wake somebody up is 2/3. Now, I need to put some exponents on here. How many W's do I want? 1 and 4. That will be the answer to the question. What is the probability that she will wake someone up exactly 3 times in the next 6 days?
Oh, we need to write 1 more.
I need 1 more row, very good. And then I need to think about what each of these numbers represents. This is, I wake somebody up 6 times, 5 times, 4 times. Is this the number I want? Did it say 3 times?
Yeah.
Would you agree that's the number I want?
Yeah.
So that's gonna be just like this, only it's a 20. And the powers are both gonna be 3s. Because if I wake somebody up 3 times, that means I don't 3 times in 6 days.
Would it be
that-
out of 6?
Huh?
Would it be out of 6?
Yeah, so 3 of 3. Now, what does C mean? I wanna wake somebody up at least 3 times. Now, this is 3 times right here.
So
What else could happen?
more?
4 times, or 5 times, or 6 times. Right? Now, some people might think, well, can we go about it backwards, Mrs. Ford? It's not really gonna save you any time, because if you go at it backwards, you still have to find no times, 1 time, and 2 times, so it's really not saving you anything. So, all right, 4 times, I got my triangle here, so this is 6, 5, so 4 times right there, 15. 1/3 to the 4th, 2/3 to the 2nd. This will take a while to type in on the calculator. 5 times would be 6. 1/3 5, 2/3 1. And then 1/3 6, 2/3 7. Now, does anything about that bottom row confuse you? You would have to add all those up, each of those terms, add them up. All right, let's see if we can get through a couple more. Find the 10th term of 2x minus y to the 12th. Find the 10th term of 2x minus y to the 12th.
Yeah, go ahead and bring that.
So the 10th term, oh gosh, I don't want to do out the 10th row. Is there another way of
10C,
getting those
10.
numbers? Yeah. The first number would be 10C10. Oh, wait.
You mean 10?
Well, I mean 12C12.
Oh, yeah.
Because I'm going to the 12 power. So the first one would be 12C12, and then 12C11, 12C10. I'm not even going to write all these down. I got to go to the 10th term. So 12C12, 11, 10, 9, 8, 7, 6, 5, 4, 3. Is that the one I want? I did that real fancy. I just counted on my fingers, right? First term is 12C12. Second term is 11, 10, 9, 8, 7, 6, 5, 4, 3. So there's my coefficient. I need a power of 2x and a power of negative y. Right? So 2x to the what power? Wouldn't it be to the 3rd? Now remember, wouldn't you count down those exponents just like I counted down this coefficient? Wouldn't you start with 12 and count down? And if that's a 3, this has got to be a 9. When you type that in, guys, please remember this is not a 2. This is an 8. Right? So it's going to be this number times 8, and then it's also going to be negative. So it's whatever 12C3 times 8 is, and then x cubed divided by 9, and it's negative. It's an 8. Number 6, how many ways can I create a sandwich, given all this kind of information? What's your thought?
So it's 3 times 4 times 3.
It's 3 times 4 times 3. Now, are there any factorials in there? No. Dollars to donuts. Somebody's going to put one in. The answer is no factorials because I'm not arranging. I'm saying I have to pick a bread. Pretend you're at Subway. How many choices do you have? 3. Then you gotta pick something else. You have 4, like a license plate. How many diagonals does a regular hexagon have?
Wait, it's not a circle.
Well, no. I mean, they're kind of in a circle, but they're not. They don't make a circle because they've got these edges. Okay, I'm going to start like Burkhart did with 6C2. Now, what's his logic? How many points are up there? 6. When I make a diagonal, I am connecting 2 of them. So this is the number of pairings that are possible between any 2 points up here. Those are the possible pairings of 2 points. What do I have to keep in mind?
As we come to the end of the day,
I gotta subtract.
I'd like everyone to pause, please, for prayer. Unfortunately, we've had one of our students, Clay Kirby's father, who passed away today. So, in remembrance of the Kirby family, to pray with them, we would like to together say the Our Father. In the name of the Father, and of the Son, and of the Holy Spirit. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Please, tonight, say a prayer for the family, and we ask this all in your name. Amen. In the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Okay, now, can you turn that off?